Okay, so we have three cables, cable tensions, T1, T2, and T3 up at the top of the flagpole. Given the resultant force for the three tensions, which is equal to negative 5K. So the resultant force is now equal to negative 500K. So this is in Cartesian vector form. Find the magnitude of each of the cable tensions. So first, let us try to identify the coordinates of the different points. So we now have the coordinates of the different points. So start with point A. So the x-coordinate, so this is the origin. So we have the x-coordinate is equal to 0. Now, the y-coordinate is also equal to 0. And the z-coordinate is equal to 12. Let's proceed to point B. So the coordinates of point B in the x-axis, so it is equal to 0. In the y-axis, left of the origin, so we have negative 8. And then your z is equal to 0. So for point C, the coordinates of point C in the x-axis, it is positive 6. So that is positive 6. And the y-axis, okay, it is equal to 0. And in the z-axis, it is equal to 0. We now have the coordinates of point D. So the coordinates of point D in here is equal to, so we have in the x-axis, so we have negative 4. Okay, it is back of the origin. And in the y-axis, it is positive 3. And we now have your z-axis is equal to 0. Now, after determining now the coordinates of the different points, let us try to express each cable tensions in Cartesian vector form. So first, let us try to express T1 in Cartesian vector form. So your T1 in here is now equal to the magnitude of T1 multiply this one by a unit vector in the direction of T1. Okay, let me see. This is your T sub 1. Okay, so we have now your T sub 1, T sub 2, and T sub 3. T sub 1, T sub 2, and this one in here is now your T sub 3. So to express T1 in Cartesian form, we now have the magnitude of T1 multiply this one by a unit vector in the direction of T1, and that is along cable AB. So that your unit vector AB is now equal to a position vector in the direction AB all over the magnitude of that position vector. So we now have your position vector AB is equal to xi plus yj plus zk. Let us determine now the components of the distance AB. So we have your x component, we have your y component, and the z component. So again, head minus tail. So it is B minus A. So it's 0, and then minus 8 minus 0. So we have minus 8, and we have 0 minus 12, and that is negative 12. So that your position vector in the direction AB is now equal to minus 8j, 0 ang x natin, minus 8z, j minus 12k. Now, so that the magnitude of this position vector is now equal to the square root of 8 square plus 12 square. And this one is equal to 14.442. That is equal to 14.442. So that T1 in Cartesian vector form is now equal to the magnitude of T1 multiply this one by minus 8j minus 12k all over 14.442. So your T1 therefore is now equal to, so we have negative 0. 8 over 14.442 is negative 0.555j. And then 12 over 14.442. Okay, so that is, so we have your T1, and that is now your J. So we have minus 12 over 14.442, 0.832. So we have T1, and that is K. Let us then express T2 in Cartesian vector form. So this is equal to the magnitude of T2, multiply this one by a unit vector in the direction T2, and that is a unit vector AC. Again, the unit vector AC is equal to a position vector AC all over the magnitude of this position vector. Again, your position vector AC again is xi plus yj plus zk. So we now have to determine the components of the distance AC. Again, your x component in here, y component, and we now have your z component. That is directed from A to C. Again, so we have C minus A. So that is 6 minus 0. That is equal to 6. Okay, 0 minus 0. That is 0. And we have 0 minus 12. That is equal to negative 12. So the position vector AC is equal to, we have 6i, the y component is 0, And then we now have minus 12k. So the magnitude of this position vector again is now equal to the square root of 6 squared plus 12 squared, or that is therefore equal to 13.416. So to express T2 in Cartesian vector form, so the magnitude of T2, multiply this one by a unit vector AC. So that is now 6i minus 12k all over 13.416. So your T2 in Cartesian vector form is now 6 over 13.416. So that is equal to 0.447, so that is T2I, minus again 12 over 13.416, 0.894 T sub 2K. Cartesian vector form of T3. Okay, after we have expressed T1, T2, and T3 in Cartesian vector form, we are now ready to determine the resultant. So the resultant is now equal to the vector sum of T1, T2, and T3. That is T1 plus T2 plus T3. Knowing the resultant to be equal to negative 500k, so we have minus 500k. So that is equal to T1, and T1 is minus 0.555. That is T1J minus 0.832, that is T1K. And then plus T2 is 0.447, T2I minus 0.894 T2K, and then plus T3, so we have minus 308. This is T3I plus 0.231, we have T3J minus 0.923 T3K. Now, so let us try to determine now your Rx. So, your Rx in here is equal to the magnitude of Rx. So, your Rx is therefore equal to, so your I minus 0.555 T1. I. So we have now your I. So that is equal to, so that is J. So we have I. So that is 0.447 T sub 2. That is now T sub 2. And then I minus 0.308 T sub 3. Let's proceed now in determining the scalar magnitude of Ry. So that is J minus 0.555 T1. Okay, so I have J plus 0.231 T sub 3. And your Rj is now equal to, okay, so we now have K negative 0.832, that is T sub 1. And then minus 0.894 T sub 2, and then minus 0.923 T sub 3. Now, since the resultant, okay, since R is equal to negative 500K. Okay, so this means that the resultant R is directed, okay, directed along the Z axis. It is directed along the Z axis. Hence, Rx is equal to 0, your Ry is equal to 0, and Rj is equal to negative 500. So it's equal to negative 500 newtons. Now, since Rx is equal to 0, then your Rx is 0 is equal to 0.447 T sub 2 minus 0.308 T sub 3. Now, similarly, your Ry, I'm going to call this one as the first equation. So your Ry is negative 0.555 T1 plus 0.231 T sub 3. Again, Ry is equal to 0. So that is equal to negative 0.555 T1 plus 0.231 T3. This is equation number 2. And then your Rj is equal to negative 0.832 T1 minus 0.894 T2 minus 0.923 T3. Since the resultant is directed along the x-axis, so the resultant Rj is equal to negative 500. And that is equal to negative 0.832 T1 minus 0.894 T sub 2 minus 0.923 T sub 3. Let's consider this one as equation 3. Now, let us try to simplify. Now, from equation 1, 0.447 T sub 2 is equal to 0.308 T sub 3. Hence, your T sub 2 is therefore equal to 0.308 T sub 3 over 0.447. And this is equal to 0.689 T3. 0.689 T3. Now, from equation 2, so this is your equation 2. So, transpose this to the other side of the equation. 0.555 T1 is equal to 0.231 T3. So that T1 is now equal to 0.231 T sub 3 all over 0.555. And this one is equal to 0.416 T3. Let's try to substitute. Now, substitute T1 and T2 in equation 3. You try to substitute T1 and T2 in equation 3. So we have negative 500 minus is equal to negative 0.832. Your T sub 1 is 0.416 T3. Then minus 0.894. Your T sub 2 is 0.689 T3 minus 0.923 T sub 3. So we have minus 500 is now equal to, if you try to get the algebraic sum of this 3 in here, then that is equal to negative 1.885 T sub 3. So that your T sub 3, multiply both sides of the equation by negative, so we have positive 500 all over 1.885. And this one is equal to 265.24 newtons. 265.24 newtons. So we have now your T sub 2 is equal to 0.689 T3, 0.689 T3, or that is 0.689 multiply this one by 265.24. That one is equal to 182.75 newtons. And then we now have your T1, and T1 is equal to 0.416 T sub 3. That is equal to 0.416 multiply this by 265.24, and this is equal to 110.34 newtons. So that those are now the values of T1, T2, and T sub 3. So we now have T1, T2, and your T sub 3. Let us now proceed to the next chapter, and that is equilibrium of particles. Now, a body is said to be in equilibrium when the resultant force is equal to 0. Or in other words, a particle is said to be in equilibrium if it remains at rest, if originally at rest, or has a constant velocity if in motion. So that is, a particle is said to be in equilibrium. So if you try to recall how we get the resultant. So the resultant force is now equal to the summation of forces. So it is the summation of forces. Since we are on equilibrium, the resultant force is equal to 0. So let us try to equate this one to 0. You try to take note in here that this is therefore the vector sum. Summation of forces is the vector sum of all forces acting on the particle. Of all forces acting on the particle. Okay, so don't forget that the body is said to be in equilibrium when the resultant force is equal to 0. So let's proceed to two-dimensional force system. Two-dimensional force system. So let's start with the coplanar. When do we say that, okay, the force system is coplanar? Okay, so the force system is coplanar when all the forces on the system lie on the same plane. So they lie on the same plane. Let us try to consider the xy plane. If you try to consider the xy plane. Considering now the xy plane, so we have, so this is your x, and that is now your y-axis. So let's try to consider that this is now your vector F1, okay, making an angle theta with the x-axis. Or we now have another vector, and this is now your vector, or force F2 makes an angle of alpha with the x-axis. Now, summation of forces of the vertical, summation of forces is equal to 0. Or, in Cartesian vector form, this is summation of fxi plus summation of fyj. You try to take note in here that fx in here and fy are scalar value. So, in scalar form, the equation of equilibrium is summation of forces along the x-axis is equal to 0. So that is to the right forces positive. And summation of forces along the y-axis is equal to 0. Then we have upward forces positive. Nagka-stream it Ken. Upward forces positive. I-post mo.
Running low and performance declining.
Now, in equilibrium of force systems, we need to know how to draw the free body diagram, or we just simply call that one as FBD. So what is free body diagram? So a free body diagram, so this is a drawing that shows the particle with all the forces known and unknown that act on it. So that is a free body diagram of a particle. So in other words, this is an isolated view of the system. Isolated view of the system that shows all the forces known or unknown and unknown which act on it. So that is a free body diagram. So if you try to go over your instructional material, so since we are dealing with particle, so equilibrium of particle, so mostly in here are concurrent force system. So these are concurrent force system. That's why we only have two equations of equilibrium before, summation of forces along the x is 0 and summation of forces along the y-axis is equal to 0. So the other equation of equilibrium will be taken later as we go on with the lecture. Now, for the free body diagram of a spring, okay, so for a spring, so the FBD of a spring, if this one in here is now, okay, so the spring is hanging vertically. Okay, so this is now your spring. Okay, so we now have your spring. Now, let's try to consider that the original length of the spring in here is LO. So that is now LO, which is the original length of the spring. Now, if a load or if a force F is applied, so this is now the force F. So, the spring will elongate or it will undergo certain deformation. And let us try to consider that this is now the length after the application of the spring, such that this is now your spring deformation. So to determine therefore the value of F, okay, so the value of F therefore is now equal to Ks. So again, your K in here is your spring constant. So this spring constant is a characteristic that defines the elasticity of a spring. And then we have your LO. This is the length of the spring, length before F is applied. And then your L in here is now the length. This is now the elongated length or the formed length of the spring, or this is the length after F is applied. So that your deformation S is now the deformation of the spring. So your deformation is now equal to the stretched length or the elongated length minus the original length of the spring. For cables and pulleys, you try to take note in here that cables can support only a tension or pulling force, and this force always acts in the direction of the cable. Okay, now, if I were going to have this one in here, so we have cable, so this is your A, we now have B, and that one is C. So this is now a load where it says now your W. So if you try to get now the free body diagram of this cable, then use at joint B. So if you try to go to joint B, so this is now your joint B. So we have the load. So we now have your BC. So this is now the tension in BC, as what we have told before, that cables can support only a tension or pulling force. And this is therefore the tension in cable AB. So that is the tension in cable AB. So it is a pulling force or tension. Now, for a continuous cable, that passes over a frictionless pulley, over a frictionless pulley, a constant magnitude of the tension. So we have a constant magnitude of the tension to keep it in equilibrium. To keep in equilibrium. Okay. Now, so let's try to consider. We have a pulley at this point. And this one in here is now your pulley. So that one is now the pulley. So we have a continuous, okay, length. So if you try to take a look now, that if this one in here is T, then this one in here is also equal to T. So that the system is in equilibrium. Okay, so we have a constant magnitude of the tension to keep in equilibrium. And then if you have a smooth surface or smooth surfaces or frictionless surfaces, you have a frictionless surfaces. Say for example, we have a body resting. So this is your body resting on a smooth surface. So this is a body resting on smooth surface. So the equivalent free body diagram, so we have your free body diagram is now equal. So this is now the body resting on a smooth surface. So it is, okay, this is now your FBD. So that is normal, or I'm just going to call that one in there as R. You try to take note in here. Take note that R is perpendicular to the smooth surface. Perpendicular to the smooth surface. In other words, this one in here is 90 degrees. So if you try to have now that this one in here is now the smooth surface. And we have a body in here. So that is now your body. So the equivalent free body diagram of this is now equal to, so this is therefore the body, hence this is therefore the reaction or the free body diagram R. So I'll be repeating that in a smooth or frictionless surfaces, now the reaction R in here is always normal or perpendicular to the smooth or frictionless surfaces. Your sample problem number 1. So a force P is supported by 2 cables. So we have your cable AC and cable BC. They are tied together at point C as shown. Knowing that the maximum allowable tension is 800 newtons in cable AC. So in cable AC, it is 800 newtons. And 1,500 newtons in cable BC. Determine the magnitude of the largest force P and the corresponding value of alpha. So let's try to determine P and the corresponding value of alpha. So first, let us try to draw the free body diagram. So this is the free body diagram of joint C. Free body diagram of joint C. This is your joint C. So we have your tension in cable AC. So this is now the tension in cable AC. This is the tension in cable BC. So this is now your tension in cable AC, and this is the tension in cable BC. Cable AC makes an angle of 35 degrees with the horizontal. And BC makes an angle of 50 degrees with the horizontal. And then we now have your P. So this is now your P, which is making an angle alpha with the horizontal. Now from our equilibrium equation, summation of forces along the x-axis, I'm going to consider that as the x-axis, and let's try to consider this one as the y-axis. Summation of forces along the x-axis is equal to 0. Then to the right, forces positive. So this is to the right, forces positive. Your AC in here is equal to, so this one in here is 800 newtons, and this one is 1,500 newtons. So we have the component of P in the x-axis is going to the left, and therefore it is negative. This is our sign convention. To the right, forces positive. So we have minus Px. So that is the component of P in the x-axis. And then the 800 tension in cable AC, the x component is going to the left. So we have minus 800 cosine of 35 degrees. Now the tension in cable BC, the x component is going to the right. So we have positive 1,500 newtons cosine cosine of 50 degrees. And this one is equal to 0. Hence, your Px in here is equal to, we have 800 cosine. Okay, negative, transpose that to the other side, cosine of 35 degrees plus 1,500 cosine of 50 degrees. So, Px, the component of P in the x-axis is therefore equal to 308.86 newtons. Now, similarly, if you try to take summation of forces along the y-axis is equal to 0, then upward forces positive. The y component of P is going downward, so we have minus Py. The y component of cable AC is going upward, so that is positive 800 sine of 35 degrees. And the component of BC in the y-axis is going up. So we have plus 1,500 sine of 50 degrees. So this is equal to 0. Hence, your Py is now equal to 800 sine of 35 degrees plus 1,500 sine of 50 degrees. So that Py is now equal to 1607.928 newtons. That is therefore your Py. So if this is now your P, that is now your P. Hence, we now have your Px. This is your Px, and this one in here is your Py. And this is now your alpha. So using Pythagorean theorem, your P is now equal to the square root of Px squared, that is now your Px squared plus Py squared. So this is therefore equal to the square root of, so we have 308.86 squared plus 1607.928 squared. So that the value P is now equal to 1637.323 newtons. Now, let us try to determine now the angle that your P makes with the horizontal. So if you try to get now your tangent of alpha, so that is equal to the opposite, so that is Py all over Px. So in other words, your alpha is now equal to the arctangent of Py all over Px. So that is equal to the arctangent of Py, which is 1607.928 over Px, 308.86. So that your alpha in here is now equal to 79.13 degrees. Okay, 4 forces act on the particle shown. So that is now your particle. So we have F1, 750 newtons, 45 degrees with the x-axis. F2, we have 600 newtons, 75 degrees with the x-axis. F3 is 1000 newtons, 60 degrees with the x-axis. And F4 making an angle of theta with the x-axis. Determine the magnitude and direction angle of force F4 for equilibrium of the particle. So again, you are required to determine your F4 is unknown, and the angle it makes with the x-axis is also unknown. Now, let's try to sum up forces along the x-axis and equate that to 0. So that is our equilibrium equation. Summation of forces along the x-axis is equal to 0. Again, to the right forces, positive. So let's start with F1. F1, the x component is going to the left. So that is minus 750 cosine of 45 degrees. Your F2, the x component is still going to the left. So minus 600 newtons cosine of 45 degrees. F3 is going to the right. So plus 1,000 newtons, that is cosine of 60 degrees. And then it's going to the right, plus F4, the component of F4 in the x-axis, and that one is now equal to 0. Hence, the value of F4x, so that your F4x is equal to 750 cosine of 45 degrees plus 600 cosine of 750, 45, 600 cosine of 75 degrees. Cosine of 75 degrees, okay, minus 1,000 cosine of 60 degrees. So we now have your F4x is now equal to 185.621 newtons. Now similarly, summation of forces along the y-axis is equal to 0, upward forces positive. So your F1 is going downward, the y component is going downward. So minus 750 sine of 45 degrees. And then your F2, the y component is going up, plus 600 sine of 75 degrees. And then your F3, the y component is going up, plus 1,000 sine of 60 degrees. So the y component of F4 is going downward, minus F4y is equal to 0. So your F4y is equal to minus 750 sine of 45 degrees plus 600 sine of 75 degrees plus 1,000 sine of 60 degrees. So that your F4y is now equal to 915.250 newtons. Now again, so this is again your F4. So we have again your F4 in here. So this is your F4. So we have F4x. This is now your F4x. That is F4x. And this one is your F4y. So this makes an angle theta with the horizontal or with the x-axis. Again, using Pythagorean theorem, f is now again equal to the square root of f4x squared plus f4y squared. So that the value of f is now equal to the square root 185.621 square plus 915.250 square. So your f is now equal to 933 points. It's 933.833 newtons. Again, to determine the direction angle theta, so we have again arc tangent of theta is now equal to your f for y all over f for x. Theta is therefore equal to the arc tangent of f for y all over f for x. So that your theta is now equal to the arc tangent of 915.250 all over 185.621. So, the direction angle of F4 is equal to 78. So, that is equal 78.54 degrees. Okay, a body with a mass of 250 kilograms. So we have the mass in here is 250 kilograms. Is supported by the flexible cable system as shown in the figure. Determine the tensions in cables A, B, C, and D. So let us try to determine the tension in cables A, B, C, and D. So first, let us try to draw the free body diagram of the lower joint. So we have the lower joint. So this is the lower joint. That is now the upper joint. So the free body diagram of the lower joint. So we have the tension in cable C, and this one is the tension in cable D. And of course, we have the weight of the body. So we now have the weight of the body. Okay, of course, that is vertical. The weight of the body is downward vertical. So this is now the weight of the body, which is now equal to W. Now, so how are you going to determine the weight of the body? So the weight of the body is now equal to mg. So your m in here is the mass of the body, and g is now your gravitational acceleration. So that is 250 kilograms. Multiply this one by gravitational acceleration, 9.81 meter per second square. So that the weight of the body is now equal to 2452.5. So you try to take note, that is kilogram meter per second square. Now, you try to take note in here that 1 kilogram meter per second square is equal to 1 Newton. Hence, your W is now equal to 2452.5 newtons. Knowing now the value, let us try to apply now our equilibrium equation. So I'm going to consider this one to be the x-axis and this one in here is the y-axis. So this is now your y-axis. So that is equal to 60 degrees. Now, if you try to take summation of forces along the y-axis is equal to 0, upward forces positive. So we have the y component of TC. So you're going up, TC, sine of 60 degrees, minus, now your W in here is now equal to 2452.5 newtons, minus 2452.5 newtons is equal to 0. So that is directed along the y-axis. So your TC in here is equal to 2452.5 newtons all over sine of 60 degrees. And this one is equal to 2831.903. 2831.903 newtons. So that is the tension in cable C. Now, let us try to take summation of forces along the x-axis is equal to 0, to the right forces positive. So, minus TD, that is directed along the x-axis. Then we have plus TC, we have cosine of 60 degrees is equal to 0. So your TD in here is equal to TC. Now the value of TC is 2831.903 cosine of 60 degrees. So we now have your TD is now equal to, we have 1415.952 newtons. Again, that is now the tension in cable TD. Let's proceed now to the free body diagram or FBD of the upper joint. Okay, so this is the upper joint. We now have the upper joint. So we have so this is so this one is your PC. This is the tension in cable A, and this is now your TA. And this one in here is now the tension in cable B. And this is now your T sub B. Knowing now the value of TC as what we have computed before, that is 28, that one is 2831.903 newtons. So this makes an angle of 30 degrees with the horizontal. This makes an angle of 40 degrees with the horizontal. And this one makes an angle of 60 degrees with the horizontal. Now, if I will now going to rotate axis, I will not going to use the ordinary horizontal and vertical axis. I will going to rotate the axis such that I will just going to consider that the line, that the x-axis is along cable, B. So that is therefore the x-axis. I'm going to consider that this one in here is now the x-axis. And perpendicular to the x-axis is now the y-axis. So I'm going to consider again that this one in here is the y-axis. So if this one in here is 30 degrees, hence this angle in here is 60 degrees. So in other words, this one in here is 90 minus 60, hence that one is 30 degrees. So if that is 30 degrees, then this one is 30 degrees, hence this angle in here is now equal to 30 degrees. Now, this one in here is 90. 90 minus 40 minus 30 is now this angle. And that angle is equal to 20 degrees. Now, I will going to write this one in here. So that this is now your x-axis. And this is now your y-axis. So that is now your y-axis. So your TB is along the x-axis. So this is now your T sub B. Your T sub B. And your TA is 20 degrees with the y-axis. So we now have your TA. So this is now your TA. So it makes an angle of 20 degrees with the y-axis. And your TC is now 30 degrees with the x-axis. So this is now 30 degrees with the x-axis. So this is now your TC, that is equal to 30 degrees. And TC is equal to 2831.903 newtons. Now, let us try to take summation of forces along the y is equal to 0. We have upward forces positive. So we have TA cosine of 20 degrees. So 20 degrees is included in the y-axis. So it's going up, so we have positive. Minus TC, because that is going downward, the y component, minus TC, which is 2831.903 sine of 30 degrees, and that one is equal to 0. So your TA is equal to 2831.903 sine of 30 degrees all over cosine of 20 degrees. And this is equal. So your TA is now equal to 1506.824. 06.824 newtons. Now, taking summation of forces along the x-axis is equal to 0, to the right forces positive. Now, since TB is directed to the x-axis, hence it has no y-axis. Now, so we have TB is going to the right. And then, TA minus the x component. So that is TA, we have sine of 20 degrees minus TC. Minus TC is 2831.903 cosine of 30 degrees is equal to 0. Hence, the tension in cable B is equal to, your TA is 1506.824 sine of 20 degrees plus 2831.903 cosine of 30 degrees. So the tension, therefore, in cable B is 2967.864 newtons. Okay, so for the upper joint, or so let us try to use the usual horizontal and vertical axis. So if I'm going to consider this one in here as, this one in here is your x-axis and this one is your y-axis. Okay, so before we rotated axis in here. So this is now your TC, which makes an angle of 60 degrees with the x-axis. So your TC is equal to, that is 2831.903 newtons. Then we have your TA makes an angle of 40 degrees with the x-axis. So this is your TA. So this is equal to 40 degrees. And your T sub B, this is now your T sub B makes an angle of 30 degrees with the x-axis. Now, summation of forces along the x is equal to 0, to the right forces positive. So minus TA, that is cosine of 40 degrees, plus TB cosine of 30 degrees, minus 2831.903 cosine of 60 degrees is equal to 0. So that is cosine of 60 degrees is equal to 0. So we now have I will going to consider this one as the first equation. So that if you try to get summation of forces along the y-axis is equal to 0, upward forces positive. So this TA, sine of 40 degrees up. TB is up plus TB sine of 30 degrees minus 2831.903. So we have sine of 60 degrees is equal to 0. So I'm going to consider that one as equation 2. So if you try to solve, let us try to solve equation 1 and equation 2 simultaneously. Solving equation 1 and equation 2 simultaneously, let us try to eliminate t sub b. So for equation 1, let us try to multiply equation 1 by sine of 30 degrees. Sine of 30 degrees. So that is minus TA cosine of 40 degrees sine of 30 degrees plus TB cosine of 30 degrees sine of 30 degrees minus 2831.903 cosine of 60 degrees sine of 30 degrees is equal to 0. And then we have equation 2. Let's try to multiply this one by cosine of 30 degrees. So that is TA sine of 40 degrees cosine of 30 degrees plus T sub B or TB sine of 30 degrees cosine of 30 degrees minus 2831.903 sine of 60 degrees cosine of 30 degrees is equal to 0. So if you try to subtract the two equations, try to subtract the two equations. Now, if you try to subtract now the two equations, this one in here is negative 0.939693 TA. So minus TA cosine of 40 sine of 30 minus your TA sine of 40 cosine of 30 is negative 0.939693 TA. TB cosine of 30 sine of 30 minus TB sine of 30 cosine of 30 is equal to 0. And then we now have 2831.903 cosine 60 sine 30 minus and minus 2831.903 sine of 60 cosine of 60, and this is equal to positive plus 1415.9515. So that one is equal to 0. Hence, your TA is now equal to or 0.939693 TA is equal to 1415.9515. So, your TA is now equal to 1415.9515 over 0.939693. So, the value of TA is 1506.824 newtons. So, let us try to substitute TA in either. So, let us try to substitute TA in either equation 1 or equation 2. So, from equation 1, so this one, minus 15, TA is 15, 06.824 cosine of 40 degrees plus T sub B cosine of 30 degrees minus 2831.903 cosine of 60 degrees is equal to 0. So we have now your TB cosine of 30 degrees is equal to 1506.824 cosine of 40 degrees plus 2831.903 cosine of 60 degrees. Hence, the tension in cable B is equal to 1506.824 cosine of 40 degrees plus 2831.903 cosine of 60 degrees all over cosine of 30 degrees. So the tension in cable B therefore is equal to 2967.864 newtons. So that is the tension in cable B.